All right, let's talk about this question. This is on AP Physics C 2024 E&M actual exam, set 2, question 2. Okay, all right. So it shows a circuit over here, which we have to analyze. So we can see that there are two resistors and followed by an inductor, an EMF, and a switch. The students are required to measure a quantity that increases with time to determine R, that increases with time. Okay. On the circuit, draw the voltmeter using the following symbol with connections that would allow the students to correctly measure the potential difference that increases with time. So I know that there are three quantities primarily which we can measure in an LR circuit. It's current in the circuit, voltage across the resistor, and the voltage across the inductor. But we know that the voltage across the inductor decreases with time, because at t equal to 0, it takes the complete EMF and then it decreases with time, something like this. On the other hand, the voltage of the resistor increases, because I know that the voltage of the resistor is EMF minus the voltage of the inductor. And since the voltage of the inductor decreases with time, obviously this entire thing will increase with time. So the voltmeter is to be placed here across both the resistors. That will make more sense. That increases with time. Describe the procedure for collecting data that would allow the students to graphically determine the experimental value of R using the measured quantity that increases with time. Provide enough details so that the other student could reply. Okay. RA and RB are identical, by the way. Their resistances are, so don't be worried about that. First off, I would like to draw an equivalent circuit here. So that's going to look like, and R are in series, right? So series means they will add with each other. So 2R. And I missed to take the inductor into account. So here I have my inductor. So the first thing which the student should do is close the switch, of course. Not close the switch. Place the voltmeter. Place the voltmeter across RA and RB combined. Second is close the switch. Third is measure, or note down readings of voltmeter at, first of all, t equal to 0 at the instant of closing the switch, so that you have the initial reading of the voltmeter. This is exactly what you will need, because that will the initial reading of the voltmeter would anyway be 0, so it doesn't really make any sense. Okay, let's first draw the mathematical equation. Maybe that will help us to determine what we actually need to measure. We know that the voltage across the resistor is given by E times 1 minus e raised to minus dr over L. Remember that EMF is known, and inductance is also known to us. So don't you think that we can just determine another value of VR at a value which is some percentage of this EMF? Because we already know what the EMF is, right? It is given to us. So maybe we can measure the voltage, and this is increasing with time. So maybe we can wait for a couple of minutes and measure when the voltage reaches 80% of EMF, because if it reaches 80%, this will become 0.8 and it will look like something like this. And whatever the time is, let's call it T1. This E and E will be gone, and we will be left with 0.8 is equal to 1 minus e raised to minus T1 R over L. And in this equation, the only unknown is R. So we can solve for it, right? So there's no need to note down the readings of the voltmeter at t equal to 0. Maybe we can, just for the sake of graphing it, but not required for the calculation. So I'll keep it, but I will add the fourth point saying that now note down a couple of other readings. For instance, you can measure the reading when the voltmeter shows 20% of E. 20% of E, 30% of E, 40% of E, 50% of E, and so on, 60, 70, 80, so that you will have enough points to graph it. And the next point is plot these points and join to draw a curve. And yeah, I think there is no need to mention this. Is there any procedure for collecting data that would allow students? Maybe we can mention this as 0.6, that now taking 80%, we can just determine the value of R. There's no need to calculate R from here because I believe there is another question which wants us to do that. Here they are asking to graph the expected trend of the data. So I think we already talked about this, the expected trend. It increases from 0 and it increases exponentially. So ideally it will start from 0 and then it will keep going on and then it will taper at some point. So this will be a horizontal asymptote which they want us to show. This will be the value of V, this will be the value of 0 ideally. So this is the expected trend which we can expect from it. Okay, and finally describe how the information from the graph in B1 would be used to determine. Now they want us to, take this situation further and what do you call it as? Uh, find the value of R. So we can do that. Uh, we are at this point. So now now rearrange this. So e raised to minus t1 r over L comes on the left side, and this becomes 1 minus 0.8. So e raised to minus t1 over t1 r over L is 0.2. Take natural log both the sides. So natural log of e raised to minus t1 r over L is equal to natural log of 0.2. So minus T1 R over L is equal to natural log of 0.2. Minus T1 R over L can be written as natural log of 0.2 is just 2 over 10, which is 1 over 5. So 1 over 5. So minus T1 R over L is 1 ln 1 over 5 can be written as minus ln 5. So minus and minus is gone. So T1 R over L is ln 5. And finally, the value of R once we cross multiply comes out as T1 R is equal to ln 5 times L. So T1 is equal to L over R ln, sorry, I have to find R. R is equal to L over T1 times ln 5. So this is how we will find experimentally using the graph the value of the, what do you call it as? The resistor. So this is how we do it. Hope that makes sense. Let's talk about the next question. Starting with an appropriate application of Kirchhoff, derive but did not evaluate a differential equation that can be used to determine the current in the inductor after the switch is closed. Okay, let me borrow the situation. In fact, I should have rather borrowed this one. Let's take this because I already found the. Oh, by the way, this should not be R, right? This should be 2R. Yep. That should be 2R, that should be 2R, that should be 2R. Please correct this, guys. Okay, that's not good. So 2R, 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 2, 2, 2. Where's that? 2. So 2 here. Okay, correction. That thing will be L over 2T1 ln 5. Good that I found this. Okay. Now let's, I think we copied the situation. Yeah. Now, as soon as the switch is closed, I think we don't need a voltmeter right now. So let's do away with this. Inductor, as per the property, it's always like, Lenz's law, oppose the cause. So plus and minus will be induced in this fashion. This is the current I. Kirchhoff's voltage law, KVL. I'm going to take a turn here starting from this point, and this is the EMF. So the first thing which I encounter in my journey is EMF, which is E, then minus I times resistance, which is 2R, minus the potential which is generated here, which has a formula of L di over dt. And I think this is it. So if we just redecorate this, bring the negative parties over on the right side so that it's positive. So the answer is going to be E is equal to 2IR plus LdI over dt. That's going to be the equation for the differential equation to find the current with respect to time. And finally, after reaching steady state, the absolute value of the potential difference across RA is delta 1. So they are only talking about RA, not the entire circuit. That's fine. Let's talk about this. So, and now they have replaced the original inductor with a new inductor that has a non-negligible resistance. The experiment is repeated. So after a long time, the absolute value of the potential difference across RA is V2. So we have to compare that. We know that after once they have reached the steady state, the entire potential of this, because the inductor is going to sleep in the steady state, right? There's no inductor. This is just a short circuit. So entire potential E is going to come across these two guys. And since they are same, this is R and this is R, so they will share half. So E over 2 and E over 2. So I know for a fact that the change in the potential or the potential across V1, sorry, the potential across RA V1 initially is E over 2. Now, if we replace this inductor with a non-ideal inductor, which means that this inductor has some resistance, so it will, at the steady state, initially the inductor was like this. So there is an inductor here and there is a resistor here. And I know that at steady state, the inductor sleeps. So there you go, short circuit, but still there is a resistor, right? So don't you think this E, which was initially shared between these two only, will now be shared between these three? Initial share of RA will obviously decrease, right? Because that is going to be shared with this teeny tiny another resistor as well. So it makes sense that whatever delta V2 is, I'm not really interested to calculate. That has to be a little less than V1 because of the introduction of this new resistor in the circuit. So I think option B makes most sense. All right, so this is how we do this question. I think this was the last part, is it? Yeah, that was the last one. So I'll see you in the next video and another question.